Welcome back. Today we're deriving some trig identities from DeMoivre's theorem. Let's get into it. So, I would encourage you to watch my video about Euler's formula. Euler's formula says that if I have a complex exponential e to the I theta, then that's equal to cosine theta plus I sine theta. And from this, there's a pretty easy to derive theorem called DeMoivre's theorem, which says that if I then have cosine of theta plus I sine theta raised to the n power, that's a binomial raised to the n power, well, by Euler's formula, cosine theta plus I sine theta is equal to e to the I theta, and I'm raising that to the n power, but by the rules of exponents, that's the same thing as e to the I theta n, but now if I treat theta n as the angle that was originally theta in Euler's formula, then by Euler's formula, this right here is equal to cosine theta n plus I sine theta n. So DeMoivre's theorem specifically equates the two pieces in red here, that cosine theta plus I sine theta all to the n is equal to cosine of theta n plus I sine of theta n. From this, we can derive some angle identities. Let's start with the double angle identities. So if I have n equals 2, then I'm raising cosine of theta plus I sine theta to the second power. Now, by DeMoivre's theorem, this is equal to cosine of 2 theta plus I sine 2 theta. But if I just FOIL, if I use the binomial theorem, and I would encourage you to watch that video, then I find that this is also equal to cosine squared theta plus 2i cosine theta sine theta plus I squared sine squared theta. And if I simplify this a little bit more, I see that on the left, in cyan, I have the real part, which is cosine 2 theta, and in blue, I have I sine 2 theta, where sine 2 theta is the imaginary part. On the right side, cosine squared theta minus sine squared theta, because that I squared becomes a -1, minus sine squared theta, that's the real part, and plus I times 2 cosine theta sine theta, which was right here, that's the imaginary part. And if you remember, again, in my video about complex numbers in Euler's formula, we know that two complex numbers are equal if and only if both their real parts are equal and their imaginary parts are equal. So I know that the cyan portions must be equal and that the blue portions must be equal. And those are exactly the identities for cosine of 2 theta and sine of 2 theta. Let's try the triple angle identities. So now n is equal to 3. So I'm raising cosine of theta plus I sine of theta to the third power. By DeMoivre's theorem, that's cosine of 3 theta plus I sine of 3 theta. And by the binomial theorem, cosine cubed theta plus 3 cosine squared theta I sine theta plus 3 cosine theta I squared sine squared theta plus I cubed sine cubed theta. I can just simplify these based on what is real and what is imaginary on the right side particularly. So cosine cubed theta, that's real. 3 cosine squared theta times I times sine theta, well, because we're multiplying by 1i here, this is going to be an imaginary term. So I know that can't be equal to cosine 3 theta. How about the next term? 3 cosine theta times I squared times sine squared theta. I squared becomes -1, so now we have no more i's in this third term. So this is a real term. This real term becomes minus 3 cosine theta times sine squared theta. And then this last term, I cubed becomes minus I times sine cubed theta, and minus I makes this an imaginary term. So cosine of 3 theta is equal to the sum of all the real terms on the right, and sine of 3 theta is equal to the sum of all the imaginary terms on the right. So cosine of 3 theta is equal to cosine cubed theta minus 3 cosine theta sine squared theta, and sine of 3 theta is equal to 3 cosine squared theta sine theta minus sine cubed theta. Again, the i's go away because we're talking about the imaginary parts, which do not include the i's. So now let's look at a bit of a larger example here. What if we wanted to derive an identity for sine of 5 theta? Again, we're going to use the binomial theorem, and I would encourage you to watch my video about the binomial theorem. In that video, I talk about a technique that you can use to remember what the binomial coefficients will be, and you use Pascal's triangle, and that looks like this. Again, you can watch the video to understand what I'm doing here. Pascal's triangle is essentially a graphic, though, where each row corresponds to a certain power that you might raise a binomial to, and each of the numbers in this row are the coefficients, and each row corresponds to a certain power of n. This would be for the 0th power of n, this would be for the first, this is for the second, this is for the third, this is for the fourth, and this is for the fifth. So it's this row we're concerned about. And since we are specifically raising the binomial cosine theta plus I sine of theta to the nth power where n equals 5, then we know that these coefficients are going to alternate in sign based on the powers of I. Specifically, they're going to go plus plus, minus minus, plus plus, because the first term is going to have no I, the second term is going to have one I, the The third term is going to have I squared, so that's -1. The fourth term is going to have I cubed, which is going to be -I, and so on. The terms that have I in them are going to alternate also. So we know that the second term is going to have an I. The third term is going to have an I squared, which gets rid of it. It creates the minus sign, but there's no more I. The third term will have an I, however. It will have a -I, and the last term will have an I. So you'll notice they alternate. If we have 6 terms in our binomial here, we have 6 terms in our binomial here, then it's only the second term, the fourth term, and the sixth term that get included. And the reason why we only include these alternating terms is because if we use DeMoivre's theorem here, this becomes cosine 5 theta plus I sine 5 theta. You'll remember we only would then include the imaginary part of the result when we sort of FOIL this out when n is equal to 5. We're equating the imaginary parts, then sine of 5 theta is equal to, by the binomial theorem, 5 cosine to the 4th theta sine theta is 10 sine squared theta sine cubed theta plus sine the 5th. That is in fact the identity for sine of 5 theta.